Hello everyone. Today we're going to look at the sine law for non-right angle triangles. So the sine law and the cosine law are two laws that were created to deal with non-right angle triangles. The sine law is used in a very specific situation with non-right angle triangles. So I've got a non-right angle triangle here, and I've labeled the sides that we're dealing with here. And let's say that you're trying to see, do I use the sine law or the cosine law here? Well, this is how you tell. You need what I like to call the sine law key. And the sine law key is a given side, numerical given side, with a numerical given angle across from it, inside the triangle, like through the triangle like this. Okay? Now, you're going to say, but sir, we don't have this angle. We technically can calculate it though. So this sometimes will be done as a little bit of a tricky situation. It's checking to see if students really understand what's going on. And you can just calculate the value of the missing angle in this case, because we know that all three angles equal what in a triangle? So 180 minus 40 minus 21 gives 119. So this is 119 degrees, and that 119 degrees is across from the side that we're looking for. Sorry, not the side that we're looking for, the other side that we're given. My mistake. Okay? So you're always looking for a number of a side length and an angle across from each other. And then, if you're given another angle, across from that is usually the side that we're looking to solve. Now in this case we actually have both of the bottom angles, so we could have solved either for this side over here or this side over here. Now let's talk about how I labeled the triangles. When you label a triangle that's non-right angled, even a right angle triangle can be labeled this way, but oftentimes because we're using SOHCAHTOA, we would label it as opposite, adjacent, or hypotenuse. With non-right angle triangles, we label the angles as capital letters, usually 3 letters in succession in the alphabet. And then we label the side lengths across from those angles as the lowercase values that match them. So if you have a capital S here, you have a lowercase s here. If you have a capital T here, you have a lowercase t here. If you have a capital R here, you have a lowercase r here. Okay? Now here's an example of an obtuse angle triangle. Let me show you an example of an acute angle triangle. So in this case, we have our key, which is the 37 degrees and the 14 units for our side length that are across from each other. And then we're given another angle, and across from that angle we're given our unknown side length B that we're looking for. Okay? Now what is the sine law? Now this is review, so you should remember this formula from grade 10. If you don't, here it is again. A over sine A equals B over sine B equals C over sine C. Now I actually have a problem with the way this is written in textbooks. I don't like the fact that they always list all 3 fractions. The only reason they're doing that is to show you that it works with any 2 of those fractions. So you're either using the A's and the B's, or you're using the B's and the C's, or you're using the A's and the C's. Okay? Now you can actually do that with any letters as long as they match top and bottom. You're going to notice in this case that our lowercase letters are at the top, our uppercase letters are at the bottom, and that's because we are doing side lengths, so our side lengths are going to be at the top. And later on I'm going to show an example where we're looking for an angle, and you're going to see that we're going to actually flip that equation upside down. So let's actually solve this first triangle up here. No, sorry, not solve, but find the letter S. Okay? So how you want to write the equation is you always want to write the unknown in the top left corner of the fraction. So where the A is here is always going to be our unknown. So our unknown in this case is little s. So I'm going to write, let me change the color there. I'm going to write little s. And as soon as I write little s, I know the bottom has to be sine of big S. Okay? Now, what's the second fractions letters going to be? Because we have r's and t's in there as well. Well, it's always going to have to be the key. So it's going to be little r over sine r in the case of above. Okay? It has to be. So now we have to isolate for little s. To isolate for little s, we're going to send sine big S over to the other side. Now, when you do that, it's going to join the r. Because it's multiplying the other side, it's top times top, bottom times bottom. Sine S is going to be a numerator multiplying r. There's going to be a 1 hiding underneath that. That's going to multiply sine r. And that's the proper way of isolating little s. And now we can just put all the numbers in there. So we've got 46 times sine 40, all divided by sine 119. We've recently discussed obtuse angles and the magic circle. So we know that sine 119 is going to give us a positive value because it's in the second quadrant. Okay, so everything here is going to work out even though we have an obtuse angle. I'm just going to double check something here. Okay, looks good. And using your calculator, you should be able to calculate that that'll give you 33.8 centimeters approximately. Okay? And that's it. That's the sine law for sides. Now, if we do the other example of this triangle, in this triangle, we're looking for little b. So like I said, you're going to put little b in the top left corner. That has to be over sine b. That's going to be equal to our key. In this case, our key is the a's. So we put the side length a at the top, sine a at the bottom, angle value. Isolate the variable. Now to speed things up, once you get used to this format of how you isolate, you can start to put the numbers in now right away, because the next step is to just put in your calculator anyway. So we're going to do little a, which is 14 times sine 82, all divided by sine 37. And that's going to be equal to 23 degrees. 23 units. We don't have units. Sorry, we don't have units for this question. So we're just going to write units next to that. All right. And because this is review, I'm feeling like I can go a little bit faster. Now, one thing that I don't know if it's review or not is, did you see the proof for the sine law? Like, where did that formula come from? So I'd like to show you that proof, and I want to show it to you with two different triangles, one that's an acute angle triangle and one that's an obtuse angle triangle, and just show you how both of those proofs work. Okay? Now, when you do a proof, you want to do it just with letters, so I'm not using any numbers here, I'm just using variables. Sorry, we don't need that quite yet. So before they had the sine law, all they had was SOHCAHTOA and Pythagorean theorem. So is there a way that we could write this as two right angle triangles? Well, if I drop a dotted line here, I now have two right angle triangles. We're going to call the spot where it intersects here D. Okay? Now over here, to do the same thing, I'd have to drop the dotted line outside this obtuse angle triangle. This is the obtuse angle, by the way. Okay? And that gives me two right angle triangles. The right angle triangle AC, and let's call this D, and the right angle triangle BCD. Okay? So watch what we're going to do here. Now, this whole side length, actually, forget about that. We don't need that. It would be little c, okay? But we actually don't need that side length because we have everything we need to do. Now, we're going to call the dotted line H. Now, the reason we're calling it H is because it's the height of the triangle, right? If you draw a dotted line through a triangle perpendicular to the other side, that becomes the height of the triangle. So, if I take triangle ACD, in that triangle, I can say that sine A is equal to the opposite side, which is H, over the hypotenuse, which is little b. If I go to triangle or BCD, I'm going to say that sine B is equal to the opposite side H over the hypotenuse A. Now both of these equations share a variable. So let's isolate that variable in both of those equations. H would be equal to B sine A, and for this one, H would be equal to A sine B. And when you have two equations that both have the same variable isolated, you can substitute one into the other. Actually, we're going to substitute it this way. Okay? So you're going to have A sine B equals B sine A. And let's rearrange it to get all of the A's on one side and all of the B's on the other. So this sine A, which is multiplying, is going to come over here and divide. And this sine B, which is multiplying, is going to come over here and divide. And there's our sine law. Let's do the same thing over here. Now it's going to be a little bit different over here. Now, in triangle ACD, okay, same triangle over here. Sine A, if I go across the triangle, gives me H over B again. Same thing as here, right? But watch what happens in the other triangle. In the other triangle, we have this angle right here, right? That angle is 180 minus B. So in triangle BCD, I'd have to say that the sine of 180 minus B is equal to H over A. Now at first glance, that does not match this one over here. But we saw that in the magic circle, if I'm talking about an angle on this side, we know that the sine value is the height of that triangle, which mirrors the height on this side. So sine of 180 minus B is sine B. They give the same answer. And now I've got the exact same thing on the other side. Okay? So I'm not going to continue that because we'd get the exact same answer. You just isolate H in both this equation and this equation, and then make them equal to each other again. So this is the proof of the sine law, very elegant proof that shows that it works for any triangle to find a side length, for any triangle that's acute angled or obtuse angled, as long as you have the key. Okay? You need that key value. Now let's look at solving for an angle. Now, you've got to be very careful when you set up these triangles, and this is going to eventually lead us to a situation that we call the ambiguous case. When you're looking for an angle, if the triangle isn't set up the right way, it is possible that when you go to find that angle, that you will get an error, that you might actually find out your triangle is actually not an acute or an obtuse angle triangle, it's actually a 90-degree angle triangle, or you might actually find out that it's got two separate answers. Now in the case that I've drawn here, we're only going to get one answer, and I'm not going to explain why yet. I'm going to wait till the next lesson for that. But I do want to show you that the sine law can be used to find angles as well as sides. Okay? So I decided to label this triangle XYZ, or Z, sorry. And I used the lowercase z here, which throws some people off sometimes. I know you're not used to cursive lettering, some of you, but this is a cursive Z, or Z, okay? So, so that's what that variable is there. Now, the first thing I'd want you to ask yourselves is, do you have the sine law key? And if you look very carefully, do I have an angle and an opposite side given? The answer is yes, so that is my sine law key. Which quantity am I asking you to solve for? Well, I've already told you we're solving for an angle. Can you see that because I'm giving you this side, 10, that across from that side is the angle that we're looking for. So the sine law always works with angles and sides that are across from each other. The key is across from each other, and the unknown and the side that's given to us in this case is across from each other. Now, normally the sine law is written like this, but our unknown is down here this time, and I said that our unknown should always be in the top left. So we're going to flip that equation over. We're going to put sine of big Z at the top, little z at the bottom, and just like before, our key value is going to go here, but the key value is going to be flipped upside down. Sorry, I don't want to put the numbers in quite yet. Like so. Now we have to isolate sine Z, okay? So that means little z has to move over to the other side. Now when you move little z over to the other side, it should actually fit right in front of sine y, okay? This is where you put the variable that came from the other side. You don't want to put it afterwards, because if you put it afterwards, what can happen is some calculators open a bracket here, and if you don't close the bracket in the right place, you might end up multiplying both of those together, which would actually be wrong. So the convention around the world is to put whatever you're putting from over here over to the other side, in this case, in front when you're isolating for an angle. So let's put all the numbers in there. We have 10 sine 32, all divided by 18. Now, some of you may have already noticed that we're actually going to have to do one extra step. If we're trying to isolate for big Z here, capital Z, we're going to have to arc sine to kill that sign. And when you're arc sining something, you always have to be arc sining a decimal smaller than 1, or you'll get an error. All right? So we should be expecting an ugly decimal here. And in fact, if you do this on your calculator, you get 0.2943, and it continues on and on. And I technically don't want you rounding that number. You can write it like this if you want, or if you're going to round it, they recommend rounding it to 4 decimal places. Okay, because even a couple of decimal places here can throw off the answer, not significantly, but by a few degrees from somebody else. So the more decimals you keep, the better. Now your calculator has a whole bunch of decimals stored in memory here. And this would be the case where you'd want to use your A and S button. If you have an older style calculator where you have to arc sine after you've put the number in, then the number is already on your screen. Just press second or inverse or shift sign to do the arc sine of that number. But I'm going to use the A and S symbol here. So we're going to sine -1 A and S to use that button on your calculator. And the answer you should be getting is like approximately 17 degrees. Okay? And I've just shown you examples, basically review, of how do you use the sine law to find side lengths, and how do you use the sine law to find angles. In the next video, we're going to be talking about weird situations with finding angles, where it's potentially going to cause you to have no triangle possible, or in the most interesting scenario, 2 possible answers to the same question. Okay? But for now, we're just going to practice the sine law as is, and I will talk to you about that video on another day.